Have you ever pondered on how computers tackle problems? This question kindles an intrigue deep within us. Computers, the omnipresent marvels that have seamlessly woven themselves into the fabric of our existence, operate on a principle that may seem convoluted initially, but unfolds to be comprehensible. Algorithms. An algorithm, in its elemental form, is a set of instructions delineated to execute a specific task. It's akin to a recipe that a computer adheres to bring about the intended result. Algorithms stand at the very heart of computer programming, forming the foundational blocks of the expansive sphere of computer science. These workhorses of computing power not only dictate the functionality of the software, but also drive the efficiency of the processes. They are the invisible masterminds behind every piece of software that we engage with every single day, extending from basic calculator operations to complex internet search engines. Their importance within computer science cannot be underplayed. They are the preeminent problem solvers, the key to making computers smart, and the pathway to technological progression. The quality of algorithms used can profoundly impact the performance and capacity of computing systems. Better algorithms can enable computers to perform tasks quicker, consume less memory, and handle larger amounts of data. In the forthcoming 7.5 minutes, we will embark on an enlightening journey. We'll plunge into the world of algorithms, dissecting this ostensibly complex concept into palatable, easy-to-grasp fragments. Our exploration is aimed at unraveling the magic that fuels our digital world, giving due credit to the unsung heroes of computer science, algorithms. Imagine an algorithm as a recipe that a computer follows to solve a problem. Think about it. When you prepare a dish following a recipe, you step through each instruction, one by one, until the dish is complete. The recipe guides you, telling you what ingredients you need, how to combine them, and in what order to do so. It is precise, straightforward, and when followed carefully, it leads to a successful and satisfying result. Similarly, consider an algorithm to be like a set of assembly instructions for building a piece of furniture or a detailed route on a map. In the case of the furniture, the algorithm would specify what parts are needed, how to put them together, and in what sequence. With a map, the algorithm might state where to make turns, what landmarks to look for, and how long each leg of the journey should take. Algorithms, like recipes, assembly instructions, or maps, are a set that a computer, or even a human, can follow to accomplish a specific task or solve a particular problem. They outline each step that needs to be taken in a specific order to reach a desired outcome. Every algorithm begins with a list of necessary ingredients or inputs. These are the data or conditions that the algorithm will use to compute a result. Like a skilled chef following a recipe, a carpenter assembling a chair, or a traveler navigating a route, the algorithm proceeds methodically through each instruction, executing them one at a time in a specific sequence. These steps could range from simple mathematical operations like addition or subtraction to more complex procedures involving multiple sets of data. Just like how a recipe could include a simple step like stirring ingredients together, or a more complex one like marinating a piece of meat overnight. Similarly, assembling a piece of furniture may involve straightforward screwing of parts or complex alignments of multiple, also share another similarity with recipes, assembly instructions, or maps. They can be expressed in different ways. Different programmers might write the same algorithm using different code, just like different chefs might present the same dish in distinct ways, or different carpenters might assemble the same furniture with individual techniques. Every algorithm, irrespective of its form, serves a specific purpose. It's a roadmap that directs the computer, step by step, on how to solve a problem. Just as recipes, assembly instructions, or maps can be expressed in different ways, so too can algorithms. They are the fundamental building blocks of computer science, serving as the step-by-step guide for problem-solving in the virtual world. Algorithms can take various forms and can be expressed in myriad ways. One of them is through flowcharts. Flowcharts are an artistic yet logical way of visually representing the process. They are essentially diagrams where every minute step of the process is represented by a box. Each box encapsulates a brief explanation of the task that is performed at that particular step. These boxes are then interconnected by arrows, forming a logical sequence. This sequential arrangement provides a linear path for the observer to follow, allowing them to comprehend the process from start to finish. Flowcharts are versatile in nature and can be used universally, giving them an edge in providing an easy understanding of the steps involved in the process. Another method of expressing algorithms is through descriptions. This involves documenting the process in English or any other human language that the user is comfortable with. It's akin to writing a detailed set of instructions for someone to follow. This technique is time-honored and commonly used among users who prefer a traditional approach to understanding processes. It's like a recipe that guides you step by step. A third and intriguing method is through pseudocode. This unique format is a blend of regular programming language and everyday language. Pseudocode is designed to communicate the process language in a manner that's easy for humans to comprehend, but also maintains the structure and syntax of programming languages. It's often used as a preliminary step for creating a draft of the actual code, allowing programmers to concentrate on the logic and algorithm before delving into the intricacies of a specific programming language's syntax and semantics. The final form of expressing algorithms is through program code. This particular representation consists of the actual lines of code that a computer can interpret and execute. Program code is the culmination of all the planning and designing of the process. It is the final stage where the process comes to actualization. The program code is what allows machines to perform complex tasks, automate processes, and ultimately make our lives easier. It is the embodiment of the algorithm, the language that computers understand, and the means by which our digital world operates. How do we translate an algorithm into flowcharts and pseudocode? This question is tantamount to wondering how we design a blueprint for a building or draft a map for a journey. Let's delve a bit deeper. The foundation of this process is grounded in positioning the concept within the sphere of digital solutions. Consider the process of deconstructing a complex issue into smaller, more manageable parts. This step is paramount in making a problem more comprehensible and computationally solvable. Here, the flowchart becomes a visual compass, a pictorial representation of the path to the solution. It's akin to an elaborate illustration that underscores every twist, turn, and decision point from the start to the finish line. Every shape, every box or symbol that adorns the flowchart carries profound meaning. Each box encapsulates a distinct stage in the problem solving. These steps are not just symbolic representations, they are distinct, precise actions that must be taken to progress. Now we approach the most intriguing aspect. These steps that are graphically represented in the flowchart can be transcribed into a concept known as pseudocode. Pseudocode, as the name implies, is a simplified variant of programming instructions. It doesn't adhere to a specific programming language, but it is structured in a way that it can be universally understood by programmers and transformed into actual code. The end product is a clear, well-organized plan that can be effortlessly translated into a language comprehensible to computers. This pseudocode then becomes the master blueprint for the actual programming code. Programming constructs such as sequence, selection, and iteration are integral to writing algorithms. A sequence is a set of instructions executed in a specific order. Selection involves choosing between different paths based on certain conditions. Iteration, on the other hand, involves repeating a set of instructions until a certain condition is met. Understanding the purpose of an algorithm is crucial. Whether it's sorting a list of numbers, finding the shortest path between 2 points, or searching for a specific item in a database, each algorithm serves a specific purpose. Understanding how the algorithm works is equally important. This involves comprehending the logic behind each step and how those steps lead to the desired outcome. Determining the correct output of an algorithm is another vital skill. This involves predicting the end result based on the given input and the steps in the algorithm. If the output matches the expectation, then the algorithm is likely correct. However, algorithms can have errors, also known as bugs. Identifying and correcting these errors is a crucial part of algorithm development. This might involve spotting logical errors in the flowchart, written descriptions, pseudocode or program code, and then adjusting the algorithm accordingly. So, in essence, an algorithm is a computer's recipe for solving problems. They can be expressed in various ways, require programming constructs, have a specific purpose, and must produce the correct output. Additionally, being able to spot and correct errors in algorithms is a necessary skill. Remember, algorithms are the heart of computer science. Every piece of software, Every computer game, every digital system at its core is a set of algorithms. So the better you understand algorithms, the better you can harness the power of computers.